Hi everyone, welcome to Module 5 for Kines 7103, Design and Analysis 1, which is taught in the Department of Health, Kinesiology, and Recreation here at the University of Utah. In this chapter, we're going to be talking about parameter estimates in a simple linear model, and specifically we're going to be talking about a linear model in which we have a single continuous predictor. So we're going to be estimating parameters in a model in which we have both an intercept and a slope. And in this module, we want to talk about different steps in that process. We want to talk about how we're going to derive those estimates, right? How we're going to actually calculate the values of the slope and the intercept themselves, how we're going to then translate that into sort of a statistical test, and how we interpret the different values of those parameters, because they will change depending on what the values of x and y actually are and the scale that those variables are on. So first, we're going to work through an example from the book in which we talk about internet access rates per household, or the average household internet access rate in each state as a function of the college graduation rate in each state. So this is the example provided in the textbook, and we want to see, is there a linear relationship between these two values across the different states? So we're going to be comparing a compact model, right, in which we assume these things are independent of each other, which is to say there is no relationship, and that the household internet access does not depend on college graduation rates. Right, so we would be estimating a constant, or the mean, for all states. And we're going to contrast that against an augmented model in which we think these things are actually related to each other. So rather than forcing this slope to be 0, we're actually going to fit a value for beta 1. We're going to say, okay, if we allow beta 1 to take some value, does that actually improve the statistical fit of our model? Visually, right, we can contrast it kind of like this. Model C is if we're estimating the mean for each state, we're going to calculate the sum of squared deviations, right? So we're going to calculate the distance between each observation and our estimate, square those deviations, and calculate the sum of squared errors. And that will be the SSE for Model C. And then we're going to contrast that against the SSE for Model A, in which we allow these things to vary as a function of college graduation rate. So on the blue line, we've actually now made our prediction conditional on the college graduation rate, and we're going to take the difference between each value and our prediction. We're going to square those deviates, and then we're going to say, all right, is the SSE in Model A smaller than the SSE in Model C, and is it smaller by a large enough amount that we think this is a statistically interesting result that is unlikely to have arisen by sampling variability alone, assuming the null hypothesis. So first, in order to do that, we need to be able to estimate the slope and the intercept. Because if we don't estimate those two properties, we aren't going to be able to calculate what our model's prediction is, and we aren't going to be able to calculate any of the sums of squared errors. So in order to do this, right, we have formulas presented in the book for calculating these two linear parameters. And so here's the formula for fitting B1, right? So B1 is our estimate of beta 1. But we're going to fit B1 from the data using least squares estimation. And this is the formula for that. And then you can see down below, when we're calculating the intercept, we're going to use B1 in our calculation. So we have to calculate the slope first, but then once we have a value for the slope, we can actually calculate the value for the intercept. And again, these are estimates based on least squares estimation. So if we use these formulas, these will give us the slope and the intercept that produce the smallest sum of squared errors. In the same way that the mean is going to produce the smallest sum of squared errors of any single number, when we have two values in a linear equation like this, these are the formulas that will give us a slope and an intercept that produce the smallest sum of squared errors. So in order to calculate the slope, we're going to need to take the sum of the xi's, right, each individual x minus the mean of x, multiplied by each individual y minus the mean of y. So what we're doing here is looking at how x and y co-vary. And we're dividing that by the degree to which x varies within itself. So in the denominator, we have x minus the mean of x squared, right? And then we are summing those squared errors. So this is a more traditional calculation of the sum of squared errors that we've seen before. And this is part of calculating the variance of x. We're not dividing it by n minus 1, but this is otherwise identical to what we would do if we were calculating the variance of the x variable. So what does it mean when we want to look at how x and y co-vary? Well, we want to see are x's that are above the mean going with y's that are above the mean. right? Because if this value is positive, right, x is greater than the mean, and this value is positive, y is greater than the mean, then the end result when I multiply those together is going to be a positive number. And if x is below the mean, right, if this value is negative, when y is below the mean, so then this value would be negative, the end result is going to be a negative number because we have a negative, or sorry, the end result in each of these is going to be a negative number, which multiplied together would give us a positive number. So if as x gets bigger, y gets bigger, and as x gets smaller, y gets smaller, those would tend to positively covary. In contrast, if these negatively covaried, what would happen is as x gets bigger, right, so for a large x, it's above the mean and we get a positive difference here, we would be multiplying that by a y that gets smaller than its mean, right? So if x is getting bigger as y is getting smaller, we're multiplying a positive by a negative, and the ultimate result of that covariance is going to be negative. So if these things negatively covary, the numerator here is going to be negative, and ultimately the slope is going to be negative. If these things positively covary, the numerator here is going to be positive, and the slope will ultimately be positive. And then what we're doing is we are scaling that to the degree to which x varies within itself, right, or the variance of x. So what we can do in R is we can calculate each of these sets of residuals. Okay, so our college graduation rates are our x variable. So we're going to create a value called x res, which are a variable within the DAT1 data frame. And they take the value of the original variable, which is college, right, shown here, minus the mean of the college variable. So that will tell us how much each x deviates from its mean. And we'll calculate a residual for y called y-res, which takes the value of internet, right, shown here, which is our y variable, minus the mean of the y variable. And you can see here we have x-res and y-res. And if we just look across at how these co-occur, you can see that we had one that had a below average internet access rate that co-occurred with a below average college graduation rate. And a below average internet access rate here, right, with a negative residual, went with an above average college graduation rate here. So we have then different products when we multiply those together. But when we sum each of these, that will give us the overall covariance between x and y, right? So each of these is an xi minus x bar times a yi minus y bar. And then the next step in the numerator would be to sum all of the values in this column to get a total measure of how much these things covary. And then we're finally going to divide that by the variance within x itself. Right, again, this isn't exactly the variance because we're not dividing by n minus 1, but it is a measure of variation. It is the sum of squared errors within x. So we're going to calculate this by just taking those x residuals and squaring them, and we'll get a column of those values here. Finally, we will add those things together and divide those two sums to get 0.8618, right? So we'll round that to 0.86 is our estimate of the slope. Finally, if we want to calculate the intercept, then we're going to take the average y minus the slope times the average x. So we can do that in R by taking the mean of the internet variable minus our estimate of the slope times the mean of the college variable, right? So the average y minus the slope times the average x, and that leaves us with 47.91228, right, or going to two decimal places, 47.91. So by hand, these would be our estimates for the slope and the intercept according to least squares estimation. And as we'll see, when we actually use the linear modeling function in R, or if you were to use the regression function in SPSS, these would be the estimates that you get out of that program as well, because these formulas are what's actually being applied under the hood when we use those built-in functions in different statistical packages. So in the book, there's actually an algebraic derivation of these least squares estimates for the slope and intercept. And I would encourage you to walk through that derivation and make sure you understand it. But conceptually, I want to focus on one slightly simpler question, which is why must this line always run through the average y value and the average x value? So take a second to think about this, but it is a fact that the ordinary least squares regression line is always going to run through the average y and the average x. And now I want you to take a second to think about why that is the case. Okay, do you have an answer? Well, first, consider that as a single value, the mean will always produce the smallest sum of squared errors, as we've shown mathematically and talked about in our previous lectures. Now, if there was no relationship between x and y, which is to say if beta 1 or b1 was truly 0, the best model of y would be x bar, right? It would be the average y. And the same is true for x. If we kind of flip the tables, we would say, well, the best value of x that's going to produce the smallest sum of squared errors is the average x, assuming there's no relationship between these two variables. So if there was no relationship, we would need a point, that's going to draw a line between these two values. So when we see how x and y covary around their means, right, we're looking at each x around its mean and each y around its mean, we're asking, as x departs from its mean, does y also depart from its mean? And if that's true, now what would have been a flat line going through the center of point y, of the y distribution gets tilted this way, right, or gets tilted this way in the case of negative covariance. So this line is going to pivot through the mean of both variables, because in the case in which they are unrelated, either if we're drawing a vertical line or if we're drawing a horizontal line, we need that point to go through the mean x and the mean y. So when we're calculating this slope, we're pivoting it about the mean of both sets of variables.